We'll start in a few minutes. I know that this is lunchtime and everybody's busy, so we start the event on time and try to finish it before 2, and leave some time for Q&A for the two speakers. Thank you for coming. I'm Kyle. I'm the CEO of Artificial Intelligence Hong Kong. Okay, so I'd like to introduce to you our group. Okay. Now, given a bit of background, I think some of us actually know us for a long time. We have been doing investor education, investor seminar for a long time in Hong Kong. One of our passion, one of our interests is to promote investment in Hong Kong. And at the same time, a lot of us founders, like including me, Fred, Eugenia, we come from science and technology background. Eugenia has a master in computer science. I have a PhD in physics. So we always, we're all interested in the technology aspect of investment or the investment aspect of technology. It works both ways. So about a year ago, our interest started to shift into fintech, which is a heated area. Now, as you know, fintech is a big area. There's blockchain, there's P2P, there's payment system, there's insurtech, regtech, blah, blah, blah. And we choose one area that I think which is extremely exciting and extremely rewarding, is artificial intelligence. So about a few months ago, actually, we changed our company names to Artificial Intelligence Hong Kong, and then we focus on AI. So these are our mission statement. You can take a look at it. But I think that at least there are two things we want to do. Number one is to promote artificial intelligence in Hong Kong and its applications. Now, a lot of people talk about AI, other people know about AI, but I think the thing that we want to do is to focus on its applications, particularly in the financial industry. Okay. And the second thing is that we want to kind of form a group we can support all the artificial intelligence engineers in Hong Kong. Actually, as time goes by, we found out that actually there's a huge community in Hong Kong that they're doing AI, and we want to create a group that we can support each other, learn from each other, and encourage each other. Okay, now, so this is our background. Now, we have done quite a few events already, starting small scale, starting last year. So these are some of the topics we covered: fintech in China, AI application in finance. Actually, just in March, we almost have our inaugural event, which is algo trading and AI investing. So we invited Dr. Kenneth Chow, who is an ex-Goldman Sachs, talk to us about how to apply neural networks into training. Okay. Now, currently we are holding some activities, so you're welcome to join. We have our study groups. We want to learn from each other. We have to help each other to learn about TensorFlow, all the advanced techniques. We are doing some. We have actually next week we are going to have somebody talk to us on research papers. So we want to know what is the frontier of AI research in the world. We also have kind of interest group in chatbots, particularly Cantonese chatbots. We have some people doing image processing and also algo trading. So so we want to create something. We don't want to stay on the level of talking and knowing. We want to create something for the community. Okay. Now, please do us a favor. Can you please take a picture? If you're not related to us, can you take a picture so you know how to find us on Facebook and how to find us on WeChat. Okay. Okay. Again, let's start the program. We are extremely delighted to have Dr. Ray Cheung from City University of Hong Kong to come to us and share us on TensorFlow. Now, as you know, I mean, Google is a big supporter of AI. There are many exciting things happening to Google, and one of the things they're doing is to build the open source for AI, which is TensorFlow. And when Google does something, it tends to be the standard. So it's very likely that it will be the kind of the standard in AI coding. So we're very happy for Dr. Cheung to share with us some of the applications and some of the background. Now, Dr. Cheung received his Master of Philosophy and Engineering and a Bachelor degree in Computer Engineering from Chinese University of Hong Kong, which is very nice, which is where our venue is. And he received his PhD in Computing from Imperial College, London in 2007. Dr. Cheung not only is a great academician, but also is a great teacher. So he received his Culture Foundation Fellowship That's his postdoctoral and doctoral research at UCLA and Imperial College. And he's currently the associate professor in the Department of Electronic Engineering at the CityU University Hong Kong. Also, not only that, I think one of the things that I share a lot with Dr. Cheung is that we really want to work very hard to link academic with industries. Okay, you found that if you look at the US, the big development in AI and a lot of the technology is how the industries and the academia work together. That seems to be work lacking in Hong Kong and actually even in mainland China. So we want to kind of do our contribution and help to fix that. Also, besides as a professor, Dr. Cheung is also the director of CityU Apps Lab at CityU, which helps do the campus-wide mobile application development. He's personally is sponsoring a lot of the activities, linking his students and with the industries. So without further ado, I will pass the time to Dr. Cheung, and maybe give us a warm up.
Thank you. Thank you, Cal.
Good afternoon, everybody. Thank you so much for coming here today. I'm so delighted to receive the invitation from AI Hong Kong to give this 45-minute sharing. Today, I would like to share my experience at City University and also some of the research work our research group has been doing. So instead of just talking about Google TensorFlow, I decided to talk a little bit more about what we call tensor computing, because I would see this is a little bit bigger, something we would actually can include Google TensorFlow in this picture. So it will be comprised of several components in this talk. So the first thing is because I know some of you here, including HL, and also I know one of my fellow classmates in Imperial College London, Anthony, is also here. Thank you for joining us today. So my research group at City University, we build architectures, okay, related to arithmetic and security. And I personally have around 20 years experience in using FPGA doing research work. And as you can see, my experience is all about this area doing computations. And currently, I'm leading a group of 6 PhD students. One of my students is here, Jack is here. And a few of my students, they graduate and they now work in China, so including Tencent in Shenzhen. They also start to work on this deep learning hardware. So this is how we train our students into the society. So my research interest is related to a few areas, but mainly it's all related to we call configurable computing. It means the computation can be restructured. So this is how we want to do. Some of my background. The outline for today, as I said, we have around 45 minutes. I do have prepared a lot of slides, so that's why I don't have time to print out the slides for you, but feel free to take some picture if you like. I will first talk about some general idea about what we call tensor computing, and then we'll talk about deep learning, and then TensorFlow as the main dish. So we'll go into some of the technical details, some of the source code. We will walk through together. We understand a little bit more, and then deep learning is a hot topic around the world. We'll talk about the applications of using deep learning. And at the end, as we said, computation can be in the form of different types. It could be in your mobile phone, it could be a computer like this, it could be a supercomputer. So how do we actually provide the existing solutions in this what we call accelerator? The first thing I would like to share is one of the research projects that we got last year. So this is a UGC tensor computing project. So this project is led by my university, the dean called Professor Hong. And I'm one of the members in this group, and my contribution in this group is mainly on hardware computations. Okay, as you can see, a number of persons in various universities, they're all mathematicians. So that means when you talk about big data, deep learning, AI, the underlying component is math. The key question behind is what is a tensor? Okay, when we want to explore, we want to know what is a TensorFlow, what is a Google TensorFlow. We got to know, we start from a number. From number, we know it's a set, and then we can get a vector. And we talk about vector, you are putting some number together, and then later on you can have what we call the two-dimensional matrix, a high-dimensional matrix. And in fact, tensor, when we deal with big data today, we need to know what kind of tensor data that we are processing. It's a form of arrangement of your data. So that means when we talk about, when we want to multiply two vectors together, we have some formula. When we want to multiply two matrices together, we have some formula. And the same question applies for tensor. However, when we talk about tensor computation, it's a new topic. How do you actually compute more efficiently? This is the key question. So that means a lot of new mathematical model should be there. For example, one simple idea is, what if the tensor data it consists a lot of zero inside? What if the data is in a very structured format? How can you process it? So this is what we want to do. However, when you want to compute this type of tensor data, it will also involve a lot of challenges. For example, the history of numerical computation, we start from the language called Fortran in the 1970s. All this is what we call the computational language. And in the current tensor computing, we need to know what is the rank, how do you do the inverse, how do you do the pseudo-inverse. There'll be a lot of challenge that you need to face. Okay, it's not just talking about you want to compute two numbers together, and it will involve a lot of what we call challenges, okay, in the mathematical model. And the next one is what we call the efficient hardware structure. So that's why today, when we want to see Google, they also designed this is Tensor Processing Unit, TPU. We'll also talk about that today because I'm very interested about hardware structure. So that's why the significance of tensor computing, it will involve a number of major areas, telecommunications, different areas. However, okay, in this slide, I would like to highlight one of the key point here is GPU. I assume that all of you would know what is GPU. And FPGA, Field Programmable Gate Array. This is not something new, but by the time when we notice Intel, okay, they include which company? Okay, Altera. Okay, when they acquire Altera, it gives a strong signal. And when ARM works so closely with Xilinx, another major FPGA company, that gives another signal. So that means eventually all our chips that we're running, it will be reconfigured. And today, when you look at the Amazon, AWS, you can upload your FPGA program onto the AWS server and then run your code, and the programming fabric will be changed. So that means, just talking about the hardware structure, it will consist of different types. However, if you go back to day one, every single processing is basically multiply and add. You just go back to the basic form. So, by the way, this is a MIC. Many integrated core. This is a chip from Intel. So that's why I would like to highlight three important layers. Okay, the first one is we need to understand all the mathematical models. Okay, apologize because I do prepare a lot of information for you. So the talk today may be a little bit rushed, but feel free, we can discuss later on today. So, just focusing on the mathematical model, it will be a bunch of areas that we need to explore. As a researcher academia, we need to address all these questions, and then we need to publish research paper. And I fully agree with Kyle that university academia should work closely with industry, because we don't want to work in our own office. The second one is how do you comprise and design your own efficient hardware, not just targeting on one application, but that can fit multiple applications. That will be our interest. And we just talked to HR recently. How can we map all these computation in a handheld device? That will be another challenge that we would like to work on. So here is some basic structure. If you look at the hardware structure computations, basically, as I said, they are basically multiply, add, and with some multiplexer. That is the primitive component. However, how do you position that? How do you determine what is the bit width? Okay, when you talk about the normal computer, this is x86, i32 architecture or i64 architecture. So that is what we call the standard bit width. Imagine the room, you allow 3 persons to go inside at the same time. That is what we call the bus width. If you talk about normal PC, it's a 64-bit today. The key question is how do you achieve the same result that you are using the minimal number of bit width? That can reduce the power, that can reduce your area, and that is a major challenge when we do the hardware design. When you talk about efficiently processing of big data, okay, when you talk about all this, the key question is imagine you are having a Rubik cube, okay, Rubik cube, and the data itself you have to compute in different angle, okay, and how do you actually lay out the computation in a time series format? So that means you are going to perform your computation one after one, or you're going to have multiple computation at the same time. And that will involve, the key question is data dependencies. Okay, you have to resolve that kind of question. So that means in all this computation, you have to design a very nicely designed processing unit. So that is how are you going to design that processing unit, and that can compute one after one. Just give you one general picture that you got some idea. If you were going to compute tensor, you got to design some processing unit. So here is one other example in major computations, even include or the TPU or some other like a GPU. At the end of the day, it will involve 2 major components. If you are learning a computer lesson 101, as we know, a normal computer will have 3 main parts, which is input, and then processing, and then output, right? And if you look at all this picture, the key component here, not just with the computation part, but it will also include the memory part, okay? And when we talk about memory, here in this slide, the major highlight is the local memory and the global memory. And how do you determine the size of this memory size, and that can give you the best performance? Okay, so memory bottleneck is another key challenge that we need to face. So basically, in this what we call tensor computation project, you have to do a lot of image processing. So that's why they back several years ago, and you can see the research group in Toronto, Alex group, they present this AlexNet, they perform all this image processing. Imagine this is what we call like some electronic machine. If you trace your angle, okay, the data point will change. And how are you going to map all this data and you still know this is the item that you are trying to do? So that means the application for all this data processing is huge. And the key question is how do we actually connect the user and with the one who is resolving the research problem? Another important idea related to what we call big data or tensor computing is the hidden information. So when we talk about tensor, okay, we say it's a multiple dimensional data. It will include, just to give one example, this is about molecular structure. So we have the gene information. Everybody, you have got your gene information. Everybody, you've got your personal information, and you've got your time access. Okay, so that means this will give you a multiple dimension of the data, and with more and more dimension, your data will increase of the data size and give you a bigger challenge of the processing. So the quick question behind is how are you going to calculate and identify, for example, this is the problematic gene information. And if you know by processing like 10,000 of patients, you identify this is a very serious gene structure, and how you're going to speculate with another patient that he may potentially suffer from these diseases. So this is some information that you can see. The machine learning, so we are stepping a little bit more about some general information about machine learning. As you can see, the machine learning history, it has been here for since the 1950s. Okay, since 1950, the old information was there. However, in 1980s, because of some new research breakthrough, people they talk about something like the bad propagation. Basically, it's like a feedback loop. You kind of process your data, and eventually, with the improvement in hardware computations, people pick up all this, and then this become a very hot topic. Okay, so this is since 1950. This is not something new. However, these few years we get more and more attentions. So when you talk about machine learning, it will basically involve several criteria, including like pattern recognitions. You need to process your pattern. It will involve, the topic is like AI. So how do you define AI? You got to learn something from your past information so that you don't make the same mistake again. So this is you're adding your intelligence to the machine. Big data, okay, people talk about big data, okay, all the time. When you talk about pattern recognition, basically we're going to recognize this is a remote. Okay, I know this is a remote. How do we tell the computer this is a remote? A lot of information that you got to process all this information. So this feels like it's more general. Okay. However, one of the very important concepts inside learning process is how do you present your classifier. Okay, include, for example, you've got a set of data, and how do you label this is a red dot, this is a green dot, and how do you find out this line? Okay, that will involve a lot of process. If you talk about two data sets, in this case, it's more simple. However, in real scenario, you become more and more sophisticated, and you got more computational power to process it. And then we involve a lot of what we call regression model. Okay, regression model. Here is one example that AI has been put in place for a Mario game. Okay, Mario game. Because I would like to give you this is a lunchtime, we should be more relaxed. Okay, so that's why here is one slide. I would like to show a video. Basic idea is how do you simulate the human intelligence use of your previous experience to avoid making the same mistake. So here is one. I hope the talk speed is okay, not too fast. Thank you. So I prepared 2 videos and 1 PowerPoint today. So this is one video.
Welcome back, Sepling here. You're watching a skilled player play Super Mario World, but this player is not human. It's a computer program I wrote called Mario. This program started out knowing absolutely nothing about Super Mario World or Super Nintendos. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of the level. It learned all of these things through a process called neuroevolution. In this video, I'm going to teach you about how Mario learned to beat this level, Donut Claims 1, what his brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mario's brain. Let's play it again, but this time we'll look at Mario's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry, I'll help break it down for you. This structure of colored lines and blinking boxes is called a neural network. It's a simple mathematical model for how a brain works, but it can produce some very complicated behavior. With enough computational power, a neural network could come close to simulating a real human brain, but modern technology isn't there yet. On the left side, you have the inputs. This is what Mario sees. It's a simplified view of the level. The white squares stand for blocks the player can stand on, and the black squares stand for moving objects like enemies or mushrooms. On the right side, you have the outputs. These are the 8 buttons that Mario is able to press by using its neural network. In between the inputs and the outputs, all those lines and boxes, those are the neural network. Each free-floating box is called a neuron, and the lines connecting those boxes are like the axons and dendrites in a human brain. At any given time, only some of these neurons and connections are actually being used, and this is what people talk about when they say you only use 10% of your brain. The neural network you're seeing is a pretty complicated one, and it got so complicated as a result of a 24-hour evolutionary learning session. So to explain how neural networks work, let's rewind about 24 hours and look at how the whole process started. This is what Mario looked like at the beginning of his training session, all the way back in generation number 0. The program is probably even dumber than you thought at this point. Often it just stands there and doesn't even press any buttons. If Mario stands still for too long, it'll cut off the simulation and try the next neural network, so it's mostly just jumping from one simulation to the next. But occasionally, the neural network says to press the right button, and the player starts walking right. Behavior isn't complicated, but it's enough to make at least some progress in the level. Let's take a look at a sample neural network to understand just how that works. This is one of the randomly generated neural networks that appeared in the first generation of the simulation. There are some green lines and a red line, and one neuron in the middle. Here's how it works. A green line is a positive connection and a red line is a negative connection. A green line reading from a black or white square will turn its output the same color. A red line reading from a black or white square will turn its output the opposite color. In this case, the green lines read from the platform that the player is standing on and make the neural network press the right button as long as the player is standing on it. However, when the red line reads a black square representing one of those Caped Koopas, it presses the A button and makes the player jump. This puts the player in a position where the green lines are no longer reading a white square, so the right button turns off and Mario just stands there. This is a really basic example that illustrates how a more complicated neural network might operate. The more lines and neurons you have, the more nuanced the decisions can be. So, how exactly do we get those more complicated neural networks? The answer is evolution. When Mario gets further right on the screen, its fitness goes up. In this case, fitness is a function of how far right it gets and how quickly it gets there. Only the neural networks that produce the highest fitness are selected to be bred, creating the next generation. It took 34 generations of genetic breeding and fitness evaluation before Mario was able to finish the level without dying and get a fitness score above 4,000. You can see there were several places it got stuck for a few generations, but it always evolved out of those ruts. Let's take a look at a few of those ruts. You can look at the top left corner of the screen to see what generation number each rut occurred on. This process of picking the fittest individuals from each generation, breeding them together, and adding random mutations very closely matches the actual process of biological evolution that took single-celled organisms and produced intelligent humans.
Yep, so I'm not going to complete the video, but I think you all get the idea. Is the machine will try to simulate with a different button, and eventually they've got this cost function to optimize the total score. So basically this is a learning process. If the Mario die, next time he will not make the same mistake. It will keep improving. So basically when we talk about deep learning, for example, this is an image. How do we determine this image actually represents a cat? You have to process through a number of what we call the convolution. And when we talk about convolution, it means like a multiplication. Okay, you're going to compute the data. It could be certain regions. Okay, this is what we call the convolution. And for some of the, like the Alex network, some of the layer is what we call the fully connected. So the data has to be transformed from a plane into a vector. Eventually, it will multiply with the data point. One of the key idea behind what we call deep learning is it will try to simulate very similar to our brain. Okay, with different region, it will try to process different part of the data information. Okay, we have an example in the next slide. Try to explain to you what does it mean. So this is one idea. For example, you've got your input image data, and when you process in this convolution layer, and each what we call the neuron layer, it will compute the data. For example, in this neuron layer, it will know, okay, the edge information. So it will try to extract all the information about edges for this image. And then in the next layer, it will compute the texture information. It will try to gather all the information related to texture, and then the object part for the next layer. And then this is finally, you get to know what it is, okay? When we talk about the deep neural network today, it can go near hundreds layers, okay? And of course, it can go even further. So that's why it gives you a big picture idea. We have different types of learning algorithm, and we also have a deep learning. And the idea is the use of more data point, it doesn't give you better performance for these neural network. But for deep learning, you get better performance. And at the end of the day, we want to get our result in the shortest amount of time. Now it comes to the key question of what is TensorFlow. Okay, this is a what we call not fairly new. Okay, if you look at the time, it's actually launched in 2015, around 2 years ago. It's open source. Okay, people they like open source because using collaborative effort, we can improve things. Now it comes to the key point. Why is it called TensorFlow? Okay, because it comprises of two words. Well, the first one is tensor, and I think up to this point, you all got to know how we define a tensor. And the flow, it means a data flow computational framework. Okay, at the end of the day, you're going to process the data, and this data could be financial data, could be image data, could be medical data. Okay, at the end of the day, how are you going to feed the information to this TensorFlow, and it will compute the information, just like the Mario is going to compute all these cost function for you. So I would highly recommend you all to give a try, because it's very easy to try. This is some source code related to Python. Okay, Python is a Python code. So when you want to use TensorFlow, it's fairly easy. You just import and then TensorFlow as a TF. Okay, this is a Python syntax. Okay, it's very similar to some Fortran or some other language. Oh, okay, yeah, just a statement. Okay, at the end of the day, you got to know what is this picture. And I think if you are able to remember this picture after my talk today, that would be great. Okay, so this is the idea. Suppose X is an image, just like the cat. Okay, X is your image. And by using this TensorFlow model, this is your TensorFlow, the very simple primitive model, you got to know, okay, what is C? By giving this cat image, I got to know this is a cat. Okay, so this is what we call the training. Okay, and you need to involve several parameters. In this case, one is called W, one is called B. Okay, of course, when the model get more complicated, you get more parameters. Okay, so the key question is how are you going to feed multiple X and you got multiple C? By performing this process, you got to find out X, W, and B. So that's why if you run your program, you got to define your, this is a floating point data type 32-bit, and you've got your data size, okay, your tensor size, and then you put this W and B initially, they're all zeros. Okay, eventually with the process, you're going to determine the step size, this training step size. So this step will be determined by using some predefined function inside TensorFlow. You got to know the step size. And after that, you're going to initialize some environment variable. Okay, you got to initialize some environment variable so that you can run your model. And the next step is you got to perform your training. You got to run your data, and what's your result? You find out what's W and B. Okay, and that is later on, if you're going to put in another new image to this X, you got to find out the result. Okay, so this is the basic idea behind what is TensorFlow and why it is so powerful. It also comes with the visualization tools. So that means you can actually see your data flow, your computational framework. So that means you can see some note. Okay, softmax is some functions. Okay, it comes with a TensorFlow. You can call different functions that you can model your applications. So that's why in this semester, I myself is supervising a few what we call final year project students. So that's why in university we call them FIP. So FIP student, the quality they will vary, but some of the really good students, they can do a lot. So this is one example. One of my students, he actually tried to model this game. I think a few of you may know this game is called Flappy Bird. It makes some good money in the App Store. So the idea is very simple. Before we run the video, you can see the game is don't let the bird die. Okay, if the bird crash on any of this pipe, it will die, or you lose the game. So the key question is how are you going to model this game in order to let the bird fly? So this is the second video that I would like to share today. So this example is using TensorFlow. Okay, this is example, a real application, a very simple one for a game using TensorFlow to learn, to train the game in order to keep the bird flying. Okay. After 4 hours training, the bird basically can move around fairly smoothly. Of course, you don't want to limit to one single game. This is another very famous game. I believe a few of us may have played this game. So the idea is don't let the small ball came off the screen. You're going to do this bouncing. So that means the real application, this is basically a toy. This is like a game. However, if a student, as a final year project student, he's able to reach this level, and you are able to give him a real project to the next level. So you can see at the end of the video, we will have some more example to show you the training. So basically, we are having some real applications using TensorFlow, and I think this is quite interesting. Next, because the time is running out, I'm going to talk more about two more things today. The first one is talking more about the deep learning for different applications, okay? And the final part will be talking about the computational framework for deep learning. So this is AlphaGo. I think most of you will know it. I don't need to explain it. Next one, upscaling. Okay, so deep learning can be applied to upscaling. What does it mean? The input in this case is this is a very closely designed image, and the deep learning engine, it will be able to upscale the image to this one. So that will be a very interesting way to provide a deep learning applications. Second one, okay, the deep learning, this is what we call coloring. Okay, coloring, and of course, if you have this gray, black and white image, and you got to know this is the pattern of a sky. So you got to map the image with this bright color, and then you got all this coloring effect. And that will be quite cool because we may have a bunch of old photos, and if we are going to use this deep learning, that can help us to color all our photos. And we've got all this link provided. These are all very established resources. A few of them coming from academia, and many of them also coming from Google. Okay, this is what we call deep learning in compression as well. Imagine the common standard in the internet when we send the image is JPEG. Okay, JPEG. So JPEG is a common standard. Today, if you talk about the original image is 14K, 14 meg already, 14 megabyte. The JPEG compresses 33K byte. This is a residual GRU format. This is 24. So that means by using deep learning, you can actually learn the image internal information that help you to compress your image. Next one, I like this one very much. The idea is how you're going to apply deep learning in arts. Okay, so now with this first image on the left-hand side, okay, you know this is the original image. Okay, and then how are we going to apply this like a paint? I'm not an artist. Okay, like this painting style to the original image, and the image, the program itself can actually learn the style and then apply to the image that you want. And I think this is very cool. This is a paper in 2016. So that's why in research academia is a gold mine. There are lots of information. And how are we going to take out all this information and apply in the real application? And I think this is fascinating. NLP. Okay, I think NLP is a quite important concept today. Like you are going to translate different language. And as a human, the accuracy for the perfect translation is still some gap. Using the traditional style, the method, you can only reach this level. Okay? By using neural network deep learning, you can achieve better, but not cross over human yet. Okay? But however, the gap is getting smaller. Deep learning in medicine. Okay, medicine. Again, this is a type of image processing. You've got your pigment, okay, on your body, and you want to know what is this. Okay. In fact, this type of image can be also learned, and the machine itself can tell you what it is. And I think this is very important because if you look at the quality, according to the research is saying, not me, the quality can almost compare with 2 dozen of doctors. So that is huge. 24 of these medical doctors, the quality. Now we're stepping into the final part for today's sharing. Time is running out. Deep hardware platform for deep learning. First one, we got to know more about GPU. One of the important measurement when we talk about all this computation is using the BLAST framework. Okay, BLAST. you're going to compute how many floating point operation per second, okay? And there are mainly two frameworks that you need to know. One is called CUDA. CUDA is belongs to NVIDIA. Okay, NVIDIA is pushing this. Okay, another standard framework is called OpenCL. OpenCL is comprised of multiple companies. They're going to map. Okay, the same design you can map into different GPU, and the same design you can even map into the FPGA as well. And of course, pros and cons. By getting bigger, the development and the promotion is also weaker. Next one, we are going to talk a little bit more on the TPU. Okay, TPU is a ASIC that recently again released by Google. So we've got two images. Okay, the first one is basically the chip. If you look at the central part, this is an ASIC. Okay, application-specific integrated circuit. So this is your ASIC. And of course, if you look at the top row and the bottom row, these are what we call memory. Okay, that get back to our previous slide. We talk about local memory and the global memory. So this is the memory. So that's why, if you look at the block diagram, you got to have all these PCIe, your bus interface. You get to send all this image information to your board, and you got to process. And one of the what we call the primitive, the core component, and one of the very common name is called kernel. Okay, the kernel size is basically determined by this what we call the MMU, matrix multiplier unit. And in this case, you're talking about 64K 8-bit, okay, matrix multiplication unit. Okay. In fact, TPU also have a new version, and the main difference is the size of this component is getting bigger, and also the memory, okay, the on-board memory will be changed. We'll talk about that later. The important concept inside this TPU will be related to some concept that we also know. For example, the Intel, you know, you've got the MMX instructions. So you got to find out some new instruction that can trigger and ask the processor to run it. So that's why you've got all these read hosts from memory. In fact, all these instructions, you can also find similar instruction in the GPU platform as well. And how you're going to activate your component, the MMU, and also how do you write back your data back to your host memory. So all this is very important instructions. When you are using the TPU, you got to run all these instructions. Next, we're going to have one performance. In fact, I got this picture from the AI WhatsApp group. It's a very fascinating group, very active. One important concept is you've got to understand this figure because it's comparing the GPU and CPU, TPU and CPU, and also, as I said, there's a TPU dash. This is a new version of the TPU. And if you compare this result, basically it will divide into two parts. The first one is talking about the total performance per watt. The power that you spend, how much computation that you are getting back. This is a key performance indicator. And why this is incremental? Because when you talk about incremental, it will remove the CPU power. Okay, just talk about the TPU and also the GPU performance. And at the end of the day, you are going to see one simple result. The TPU is very, very good, very fast. And as a researcher, what is my interest? I would like to know, is there anything better than TPU? How are we going to design that hardware? And that's more important. So, in Hong Kong, I got to know China is doing very well. So China is already taking this step ahead. If you look at this design from Institute of Computing Technology, Chinese Academy of Science. Okay, so they already designed another new chip. Okay, this is in 2016. So they've got what we call the vector processing unit. They've got like a long instruction processor, fetch unit, decode unit, and then this is basically a processor. And then you've got some internal vector unit, matrix multiplication unit. Because we understand the tensor processing unit, with this picture, you've got to know the core component is this matrix unit and also the vector unit. It will perform around 10 times faster than the GPU. So I think this is one of the directions that we're heading towards. FPGA. This is another design from Fudan University, 2016. So FPGA, I think we got to know what's FPGA. You've got your host PC, and then you've got this is a 10 gigabit Ethernet, and you've got your on-chip memory. This is an 8-layer in AlexNet. So basically, this is again mapping the computation in FPGA, and one of the highlights, as you can see, this research group, they are from China. So we are competing with them. Okay, in Hong Kong, we are competing with them. This is one of, I would say, a very important slide. The credit goes to my PhD student, Jack. So he did a very important search with all the related research conferences because it takes shorter time to release. Usually the time frame is about half a year. So some result is there and then they publish. So you can see mainly these deep learning hardware design, they come out in 2015, 16, and this year. And you can see they run on FPGA, ASIC, GPU, different type of platform, and all of them will have different types of very special behavior. Okay, we don't have time to go cover all this. I'm more than happy to discuss with you all later on. But one of the performance indicators is again the throughput. How many operation per second? This is a floating point operation. Some of them they're integer operation. So this is how are you going to measure how good your hardware is. So we also perform our own FPGA design. So in our lab, as we said, we have a 6 PhD student. So we are going to design our own computational kernel, performing all these convolution module, some operation, and eventually you're going to see we got to connect our data back to the Ethernet, and then we are able to fabricate our ASIC chip as well. So in this example, you can see for the image, the input line is 1. We design our own kernel, and then we are going to compute 5 partial results at the same time, and that could be scalable. So we are designing a long